Welcome to standard error in Desmos. So recall that a standard error, or when it comes to scatter plots and regression, the standard error measures the typical error between the actual points and the regression line. So if we just drew our very quick scatter plot, with our regression line through the middle, recall that the error is the vertical distance between the point and the line. Right. And so we're looking at what is a typical error. So this is our error, is that vertical distance between a point and the line, and standard error is the typical error. All right. So let's go ahead and just take a look at an example. We'll go over to Desmos, and I'll show you how you can actually find the standard error and more closely what it means in the graph. So in this example, a study was run on the relationship between age in years and height in inches of elementary school students. So children between 5 and 10 or 5 and 11. Data was collected from 20 students and can be found at this Desmos link. Our job is to find the regression line, correlation coefficient, and standard error, and then predict the height of a child at age 8 and explain how likely your prediction is to be accurate. So let's go ahead and just jump over to Desmos. So if we go over to Desmos, we have here our list of data values on the left. So that first child is age 6, height 48 inches. And we have a scatter plot on the right. So using our usual tricks, we can go ahead and find our regression line. My data was labeled X1, Y1, so we can type in Y1 and then our squiggle, A plus B, and then X1. And it finds our regression line for us. Then off to the side, we have our R as usual, right? So I'm going to go ahead and just take a quick screenshot of my current screen. Right, so we have our regression line and we have our R. So notice that it also has residuals and labeled E1. That E1 is our errors. So if I plot my error, I scroll up, it's saying that our first point at 648 is 2.23 away from the line. So if we look at our graph, 648, I'm going to go ahead and do some drawing on the screen quickly. The point at 648 is this point here at 6, a little above our line. And if we looked at that vertical distance from the line to that point, it's a little over 2, right? So that distance of 2 is precisely what this 2.237 blah, blah, blah is referring to. So those E1s are our errors, how far off each point is from the line. Points above the line have a positive error. Points below the line have a negative error. If we wish to, I'm going to take a quick screenshot again so I can transfer to the notes. If we wish to calculate the standard error, what we can do is we can just tell the Desmos to calculate the standard deviation of that E1 list. So I wish to find the standard deviation. So here is my standard deviation under functions, under the statistics label. And I want to find the standard deviation of the list E1. So this tells me I have a standard deviation of 1.72. I am going to call this E equals, so capital E equals this 1.72. This is my error. Now my regression line itself is y equals 30.8136 plus 2.49x. I'm going to just try something here. I haven't actually ever tried this before. If I type in y equals a, oh, it is there, good, plus bx, that should just give me my regression line. It's right on top of the other line. Now, if to that I add my error, it just shifts the line up by the error, by my standard error. And then if I do the exact same thing, y equals a plus bx, but this time minus my error. I'm going to change these both to, let's do these both in red. Notice that most of the points fall between those two red lines I just drew. So most of the points fall sort of within that standard error. I'm going to zoom out just a little. And then we have some points below the bottom red line and some points above the top red line. So our typical points fall sort of trapped in between these two red lines. So this is what standard error is doing. It's giving a little wiggle room below and above, saying, okay, our typical points, our typical individuals do fall sort of within this band. All right. So let me take one more picture so that we can transfer this all over to the notes. And then let's go ahead and just go straight back to our notes. So coming in our notes, the very first thing we had was just a scatter plot and regression line. Okay. So the very first thing we did, I apologize for the zooming in and out. Our step one was to find R, and the regression line. Right. So we did our usual trick. This is what we enter. Was that y1 squiggled a plus bx1. And then our R is 0.9305. And then the A and B told us that our regression line is y equals 30.81 approximately plus 2.49x. So this is what we pulled from the regression line. Now, from here, step 2 was to click on plot under the word residuals. So I'm just going to highlight this button. So we're clicking on plot. Was our next step. What this will do is this calculates all of the errors, or calculates the error for each point. And again, we did this right? So here are errors. Right? So again, if we focused on the first row, right, that's 648 was our point here. And if we drew our error, the distance between the line and that point, that error is that 2.23 that we found above. So we can see this point right here. Right, so that was finding our errors. Our next step was to find the standard error. To do this, we just enter STDEV and then parentheses E1, since our errors were in the E1 column. So we did that. I apologize for this zooming in, zooming out that's going on, right? So here is our standard deviation, or our standard error. What your book typically refers to as a capital SE. This is 1.728, or approximately 1.73. The two lines that I plotted, this is shifting the regression. The first, we shifted the regression line up by the error. Or by the standard error. And that second line, y equals a plus bx minus e, we shifted the regression line down by the standard error. So again, what we saw here is that most of our points, or our typical points, fall between those two shifted lines. So we have that our typical points fall between the two shifted lines. This means that typical points fall sort of within plus or minus a standard deviation of the line's prediction. So our final step here is to actually go ahead and make our prediction and talk about its accuracy. So our step 4 is to make the prediction and determine its accuracy. So our original request, I apologize for the scrolling. I will come back to this in just a moment. The original question asked us to predict the height of a child at age 8. So we want to predict the height of the child at age 8. What we will do is we will make an initial prediction. Using the regression line. So we have age 8 corresponds to x equaling 8. Our regression line was y was equal to, again, I apologize for the scrolling. Our regression line y is equal to 30.81, or we'll just go with 30.8 plus about 2.5x. So y is approximately 30.8 plus 2.5x. We will take this 8, plug it straight in for x. So we are looking at y is approximately 30.8 plus 2.5 times 8. Order of operations, we do that 2.5 times 8 before we do the addition. 2.5 times 8 is just 20. So we are looking at 30.8 plus 20, or approximately 50.8 inches. So our initial prediction, or our base prediction, is that a child of age 8, or an 8-year-old child, is predicted to be 50.8 inches tall. Now, none of our 8-year-olds were actually 50.8 inches tall in this study. So we know it's not always accurate. So this is where the correlation coefficient and the standard error come into play. So using the correlation coefficient, which was R equals, again, I apologize for the scroll. R was 0.93. Right? Using the correlation coefficient, R equals 0.93. We know that this relationship is very strong, or is strong. And so what this tells us is that we expect the predicted 50.8 inches to be fairly accurate. So we expect the prediction of 50.8 inches to be fairly accurate. But again, what does it mean to be fairly accurate, right? So, right? But what does this fairly accurate mean? In this case. Right? So then this is where wiggle room is. So here we will give ourselves some wiggle room. So we can give the prediction some wiggle room. With the standard error. Okay. So what we can do is we can take our base prediction and do our plus or minus the standard error. Our base prediction was 50.8. Our standard error was what, 1.223? Sorry, that wasn't it. Our standard error was 1.72, or about 1.73. We'll just go with 1.7. So plus or minus approximately 1.7. So this will split. We'll have a 50.8 minus 1.7, a 50.8 plus 1.7. 50.8 minus 1.7 puts us at 49.1. 50.8 plus 1.7 puts us at 52.5. So what we get here is we predict typical 8-year-olds to be between 49.1 and 52.5 inches tall. Or in other words, our prediction of 50.8 inches is likely to be within 1.7 inches of the child's height. Here it's likely. Note, this is not guaranteed, right? So this is just a typical child. It's not all children. So just a note. There is still no guarantee. The prediction with wiggle room is accurate. Right? It just has a better chance of being accurate. Right? So this is standard error, how we can find it, how we might interpret it, how it helps giving us our wiggle room. And that is all for standard error.